Hello, my name is Iftikhar, and my project is Model Predictive Control Strategy for Grid Interactive Efficient Commercial Buildings. To explain what a grid interactive efficient building is, let's start with a typical building, shown by the blue line, where energy peaks sharply at midday due to air conditioning, lighting, and occupancy. By improving efficiency with better insulation, LEDs, and other measures, shown by the yellow line, the peak reduces, but the overall shape remains similar. Adding solar panels, shown by the green line, changes things further, sometimes dropping midday demand below zero and creating the duck curve with a steep evening spike. Finally, the red line represents a grid interactive efficient building. Here, batteries and smart controls shift energy use, respond to grid signals, and even share power with neighboring buildings. My main aim in this project is to achieve this red line, creating a smooth energy curve, lowering energy cost, reducing peak demand, and supporting a stable, sustainable grid for everyone. So, how do we control the building to achieve the desired energy profile? That's where Model Predictive Control or MPC comes in. MPC turns the building into a smart, energy efficient partner for the grid. Using a digital twin, it predicts energy needs based on weather, solar generation, battery state, grid signals, and occupancy. An optimizer then shifts or sheds loads to reduce peaks and energy use while keeping occupants comfortable. Control actions like adjusting AC or charging batteries are updated continuously in real time, adapting instantly to any changes. In this project, two simulations are done using MATLAB and IES VE software. First, a building to grid scenario applying strategies like real-time pricing, demand limiting, load shifting, and shedding. And second, a building to building scenario where multiple buildings share and exchange energy. Now, to look at the results after optimization, this first graph shows real-time pricing. You can see how the daily energy cost drops as a system avoids high price periods using solar PV and battery power shown in orange to cover most of the building's needs. Next, in the demand limiting case, the peak demand that originally reached around 200 kilowatts is now capped to about 95, successfully shaving the peak load. Then we have the load shedding where the optimizer temporarily reduces power use from about 200 to 100 kilowatts during specific hours, lowering strain on the grid. In load shifting, energy use is moved from evening peaks to lower price morning hours, balancing the demand. Finally, in the building to building case, you can see how the buildings A, B, and C share and exchange energy through imports, exports, and storage, demonstrating how interconnected smart buildings can collectively create a more efficient, flexible, and resilient energy system. Thank you.